Next is semiconductor laser. It's very interesting. Okay, so semiconductor laser is commonly used laser, and it has some extra applications, additional applications and advantages are there. But you should know basic things of semiconductor to understand working of a semiconductor laser. We'll discuss that. Semiconductor laser often referred to as a laser diode since it operates like a diode. Semiconductor diode, you should know, with current flowing in the forward biased direction of the junction. So, and the semiconductor diode should be in forward biased condition. There are two types of bias. What forward? One is forward biased, another one is reverse biased. So this laser, a lasing action to happen, it has to be forward biased. So there will be a depletion junction or what depletion layer that we will discuss. And by injecting charge carriers into the region of space defined by the junction, recombination radiation can occur, provided this current injection is strong enough, a population inversion can be achieved. So that we will discuss in the further slides. And most commonly used material is gallium arsenide. This is the active medium. Okay, the gallium arsenide is the best semiconductor which we can use. We can use it for lasing action or laser manufacturing. Gallium arsenide. Silicon is there, germanium is there, but that it can't, or other semiconductors are there. But gallium arsenide is the specific material we can use it for generating lasing action. That you have to keep in mind. The two characteristics. One is electrical pumping. That is outside one source source we will use to generate energy. Either it can be a light source or some other source. Electrical pumping and compact laser design coupled with maturity of semiconductor manufacturing processes enable laser diodes to gain number of advantages over other lasers. It has specific advantages over liquid lasers as well as gaseous lasers. Next is some small sort of discussion or description on semiconductors. So there are three different types of materials: conductor, semiconductor, insulator. So conductor, it can easily conduct electricity. Insulator, negligible. Conductivity is negligible. And in between becomes semiconductor. The performance will be in between conductor and semiconductor. Oh, sorry, insulator. So what are the examples of conductor? Silver, very good conductor of electricity. Copper, gold, aluminum. Insulator, wood. It won't conduct any electricity. Glass, Teflon. These are some of the examples of insulators. Now, semiconductors. So silicon, germanium, gallium arsenide. So silicon is a good semiconductor. Germanium also a semiconductor. Gallium is another semiconductor. And for the lasing action, we are using gallium arsenide. Now, so there are two different types of semiconductors. All these things you learned in your secondary time or your 10th standard, 10th, 11th, 12th. You might have covered all these things, but it's a recap. Okay, semiconductors are of two types mainly: intrinsic, extrinsic. Extrinsic means what? Intrinsic, extrinsic. What is the difference? Intrinsic means in pure form. There is no impurity. Extrinsic means we are adding extra foreign materials and it to improve the conductivity of the semiconductor. So while adding what that process is called extrinsic, means we are enhancing the performance of a semiconductor by adding external atoms or outside atoms or other atoms. Intrinsic means in pure form. Silicon means only silicon atoms will be present. Extrinsic means apart from silicon, we will add outside material to improve its conductivity. Okay, that process is called doping. That you might have learned doping. So if we add that as a result of that doping process, we can generate p-type semiconductor as well as n-type semiconductors. So p-type means the charge carriers, the majority charge carriers will be positively charged. That means holes. In n-type semiconductors, the majority charge carriers will be electrons. That is the difference between p-type and n-type. P-type positive and negative. Electrons negatively charged, holes positively charged. You just imagine like that. So p type, n type. So p type means charge carriers is majority charge carriers is holes. In p type, minority charge carriers will be electrons. So don't confuse. N type, the majority charge carriers will be electrons and minority charge carriers will be holes. So to get a p-type semiconductor, what we have to dope with trivalent uh, atoms. Okay, silicon, you can see silicon, this is atomic number is 14 and there will be total 14 electrons, and in the outermost shell or valence shell 1, 2, 3, 4. 4 are there. To get the stability, another 4 it should get. Then only it will become a stable, it will become a it will stabilize. Okay. So in pure form, silicon, this is one, sorry, this is one, this silicon, this belongs to, okay, this one, two, three, four, okay, and another one. This silicon has another, this one, yes, one, two, three, four. See, you can see here, and another silicon. If I am selecting this one, then it has uh, one, two, three, sorry, one, two, three here. It is four. So actually, this second one of it is sharing. Both are shared. This and this shared by this silicon, and this silicon shares this one. So likewise, if you take another two here, this another it is through sharing of electrons, it is attaining the stable condition, stabilized condition. Okay, so this silicon is getting only, actually this is having what, this is having only what, this is having one, two, three, four, but the other four, it is getting from here this side, one from left side, one from right side, one from front side, one from back side. Okay, so this is called as pure form, pure form of semiconductors. But p type or n type, first we will discuss about n type. N type means majority charge carriers will be electrons. Okay, so this is pentavalent. So this is pentavalent. Pentavalent means what? Pentavalent means outermost shell has 5 electrons. So that 5. So phosphorus 1, 2, 3, 4. This is the extra. So if you dope with a pentavalent, one electron will be excess. This excess electron will act as the charge carrier. And in the p-type semiconductor, boron we will take. P-type, what p-type, the holes are the majority charge carriers. So there will be a vacant position. So to create a vacant position, one electron should be less. So we will dope with trivalent atom. Boron is the example. Okay, boron is the example. So there will be a hole. So that hole will be the majority charge carrier. So p type, n type completed. So this is the thing. So that is called extrinsic semiconductors. P type, for example, aluminum, boron, gallium, trivalent atoms. P type means we have to dope with trivalent atoms. And N-type means we have to dope with pentavalent atoms, arsenic, antimony, phosphorus. Okay, pentavalent 1, 2, 3, 4, 5 electrons are there. See, if the pentavalent means excess, you can see the excess electron here, majority charge carrier. So this majority, so this excess electron, this atom is ready to give that, donate that electron. So it is called as donor atom also. That phosphorus is a donor atom there. It is having one extra electron because already it has satisfied that for sharing, because with the help of that sharing, valence shell is having 8 electrons. This is actually excess. So it is ready to give that, donate. So donate means once it is, if it donate means it will get positive charge. Okay, so that is the thing you have to keep it. But boron means, or aluminum, this there is a hole, so it will accept. So it's an acceptor atom, and once it accept, it will become negative ion. Donating, that we are giving something, so we are having, that person is having positive symbol, and if you are